Xiao Hu. I'm a research fellow in the logic program. I'm also the incoming assistant professor in the University of Waterloo. Today, I'm very happy to share some interesting direction in the database theory and algorithms, which is the join algorithms meet new constraints, scalability, latency, and privacy. Okay. In the relational database, the join is a fundamental operator that can link the information stored in different tables together. So given two tables with common attributes, the join operator will find all pairs of tuples with the same value on their common attribute. And if we have more relations, we can use the join operator to express more complex analytical queries. Okay, in this relational knowledge graph, each node is an entity and each edge is labeled with the interaction between these two entities. And we can store the edges with the same label in one relation and ask join queries. For example, find all people who like something in the Louvre Museum. Okay, use this three-way line join. This problem in general is NP hard if not assuming the query size as a constant. So people focus on the data complexity of this problem. And the traditional goal of the research for the join processing is to find the most time-efficient way to report all the join results. In the last 20 years, the need to process and analyze big data has invigorated this traditional research area with a lot of new challenges. For example, large volume data cannot be stored and processed by a single machine. People have developed massive parallel systems such as MapReduce and Spark for data processing. Then how to design join algorithms that can scale to more than hundreds or thousands of machines? We can also use a theoretical model to capture the abstract, the architecture of those systems. So given an input join query and the database distributed over the machines, the computation process in rounds. And in each round, the servers can communicate with each other and then perform some local computation. The complexity of the algorithm in the massive parallel computation model are first measured by the number of rounds and then the load, which is the maximum size of message received by any server in any round. So here the target is to design join algorithm that achieve the optimal trade-off between the round complexity and the load complexity. The second challenge is that data is generated at a very high speed. Then how to deliver timely answers to the users. Similarly, we can have a theoretical model to capture the settings. So given a join query and the database, the target is to design a data structure, okay, that can be updated efficiently with the updates to the data. And also whenever the query answers is required from the user, we can enumerate the query answers from the data structure with delay guarantee. So the delay here can bound the waiting time between consecutive answers. Okay. And here the theoretical target is to study the trade-off between the pre-processing time, the update cost, and also the delay in the enumeration. The third challenge is that data usually comes from multiple resources and contain sensitive information. So people have paid a lot of attention to the privacy issue, then how to evaluate a join query without leaking the information of the underlying database. We can see the scenario that even both the input data and the join answers are encrypted. Okay, the adversary can still learn something by observing the behaviors of the join algorithm. So what does the behavior mean? So in a sequential RAM model, it could be the sequence of read and write operators to the main memory. Or in the massive parallel systems, it could be the send and receive communication pattern of the servers. Here, the goal is to design join algorithm whose behavior does not lead to the distinguishability of the input databases. And if you want a different level of protection of the privacy, you can also assume differentially oblivious algorithm for the label input database. Okay, So beyond the natural join, there are many interesting join-related problems I have worked on. For example, the similarity join, join aggregate queries, sampling over join, temporal join, difference of join queries, and generalizing synthetic data set for the join queries. Okay. If you catch any interesting keyword, feel free to talk to me. Yeah. Thank you.
Any questions? Okay, excellent. We have one question.
Yeah, so how about the joins in fast data, like streaming data joins? Is that something that you're considering?
Yeah, for example, we have some counting query on top of the join results, and we want to release a synthetic data set, for example, which is differentially private, and then still provide some accuracy guarantee for answering counting queries over the join result over the synthetic data.
Thank you.
Thanks.